All right, hello and welcome again to another exciting and amazing chemistry problem tutorial. In this video we will work out problem number 3 from page 38, which some of my students we did in class, others we did not. So we're just going to work the whole thing from the ground up and you will not have missed anything. So let's read the problem first. We're given a reaction. We have diatomic hydrogen reacting with diatomic iodine to form HI, and we have 2 over here. So experimentally, we're told that the reaction is first order. This WRT means with respect to H2, and also first order with respect to I2. Notice that this here, being our overall reaction, indicates that this is going to be sort of the thing that we are concerned with, and these mechanisms down here are not as certain. So let me explain what that means exactly. The overall reaction, we don't know exactly how it happens, but we're interested in that. So we call this type of a problem a mechanism problem, or at least that's what I call it. In this mechanism problem, we have proposed 3 steps that we think explain this reaction. We're saying down here, okay, we have diatomic iodine, and then it breaks into 2 iodine atoms. Then an H2 comes along and reacts with one of those iodines, and it forms H2I. Finally, an H2I reacts with another iodine that's floating around, and they form 2HI. So in this mechanism problem, we are claiming we've come up with this great idea to explain how the above reaction happens. So first off, I think I already said first off, so how about second off, let's determine the rate law for this overall reaction. We cannot use the coefficients for an overall reaction in writing a rate law. What we have to do is look at the information we're given in the problem and base it off of that. So down here, how about off to the side, next to the reaction, we can write the rate of the overall reaction is equal to K, that will be our rate constant. And now we have our reactants up front here. It says that it's first order with respect to H2, and also it says it's first order with respect to I2. So we can put 1s there. We don't really have to put 1s up here, but just for clarity, let's put them up there for now. And we can also see that our overall order for this reaction is 1 plus 1, so the order is 2, or let's say second order. All right, so we have a couple of things we're going to work on in this problem. There are two things that have to be satisfied in order for our proposed mechanism to be valid. Number 1, we need to make sure that the steps add up to the overall reaction. Pretty simply, if we have all these steps over here and they don't add up to our overall reaction, then it's kind of like, well, what are we doing here in the first place? This is what we're interested in, and if these steps don't add up to our overall reaction, basically our entire mechanism is pointless. So, in most cases, you have to imagine that the steps are going to add up to the overall reaction, but you never know. If they don't, then we're done. We can say, all right, well, clearly this set of mechanisms is no good. But if they do add up, we have a second thing that we look for, and that is to see if the rate of the mechanism or mechanisms match the overall reaction. So what does that mean exactly? When we're talking about rate, we're going to go to our rate law over here. So let's circle this to sort of keep it apart from everything else. When we find our rate law for these mechanisms, we need to make sure that it's the same order. So we see up here, we found that our overall reaction is second order. We found that experimentally. We need to make sure that for these mechanisms down here, that they are also second order. This part can take a little bit longer. So if indeed this adds up correctly, we're going to move on to number 2 and make sure that it matches up. There's only one condition that we have to make sure to follow, and this is going to make this problem a little bit more mathematically challenging. When we are determining the rate law for our mechanisms, it has to be in terms of our reactants for our overall reaction. So to sum that up, when we find the rate law for our mechanisms down here, it has to be in terms of H2 and I2. It can't be in terms of anything else over here except for H2 and I2, because those are our reactants for our overall reaction. We can't really compare them if they aren't talking about the same thing. So it'll become more clear what I mean by that as we go on. Let's begin. First, number 1, do the steps add up to the overall reaction? There's a number of ways you can do this. You can just eyeball it and cancel out what you have multiples of. For example, I can just see that I have 2 iodine on my product side, and I have 2 iodine on my reactant side, so those are probably going to cancel out. For clarity, I'm going to just add everything up underneath, and then we can cancel what's on the left and what's on the right. So let's go ahead and do that. Also, I'm going to label my 3 steps, 1, 2, and 3. Seems like a good plan. Alright, so from the left side, step 1, I have I2. Below that, from step 2, I have H2 and I. Then we're going to have H2I and another I over there. Then on the other side of this, we're going to have 2I plus H2I, and then, oh, I'm running out of room. And then we're going to have 2HI over here. So I apologize for crowding myself. I should probably take a little bit more space. Alright, but hopefully you can see that. If not, then, I don't know, squint, maximize the video. If only there were an option to clarify my handwriting. Ha ha ha. Oh man, what a lame joke. It's in the middle of my video, so I can't easily edit that out. Alright, I'm not going to start over now. Let's keep going. So we can see, as I said earlier, that we have 2 iodine over here on the right. We have I and I on the left, so those are going to cancel out. Let's grab a colored pen or something. Okay, here we go. We have, all those have canceled out. Notice also there's an H2I over here on the right and on the left. Those are going to cancel out as well. So what do we have left over? We have I2, H2, and 2HI. Okay, I2 plus H2 going to 2HI. That's all that's left over, and hey, that's great. That's the same thing as our overall reaction. So this entire problem may yet match our desired reaction. All right, so we can go to our number 1 over here and say, yes, we did it. We have satisfied one of the 2 steps. Fantastic. Now, that means we have to go on to number 2, which is to make sure that the rate of the mechanisms match the overall reaction. So here you'll notice that I have these words off to the side, fast, fast, slow. And what I can tell you about this is that whenever you see this fast, fast, slow, essentially this is going to be the type of problem you're dealing with that we're doing right now. There are a lot of different types of problems where you can see multiple steps in this unit, but when you see the speeds, it's going to refer to this type of problem we're doing now, a mechanism problem. So as we look at this, you should notice that there's only one slow, and this is sort of a relative issue. There are a lot of different metaphors for how you can conceptualize this. The one I like best is as follows. Imagine that, or don't imagine, I myself have a family. I have a wife and I have 3 kids. I have 2 of my kids which are able to walk. They are, they're older. But I have 1 kid who is not so much a kid as a baby. He's 9 months old and he likes to fall over and hit his head. It's a bad scene, man. But anyways, let's say that my entire family we want to head out on a walk. As we leave the house, I say to every member of my family, let's go on the walk. Our end goal is that park over there. All right, so I set out at a good pace. My wife sets out at a good pace. She's probably a little faster than me. My kids, my 2 older kids, they love running and scampering around, but my little baby sitting there on the pavement is definitely not going to go very quickly. And so in this metaphor, my baby is the rate determining step. In reactions, it doesn't matter if this one's really fast, this one's not that fast. The only thing we're really concerned about is this slow step. We call this the rate determining step, and this step is our baby step, if you will. So again, the point of that metaphor is that no matter how fast other things are going, that baby is going to be limiting how fast the overall reaction actually goes. All right, so hopefully that helped. If not, you learned some things about myself and my babies. So that's good. All right, so what do we do with this step 3 over here, this rate determining step? Well, one thing that's very nice about this type of mechanism problem is that you can do something you haven't been able to do up until now. When you're writing the rate law, you can actually use the coefficients here when writing it. So we can write, for example, the rate law for each of these actually. So we're most concerned with step 3, so let's do that. You can still see that, that's good. So rate 3, our baby step, the rate that determines how fast our reaction is going to go, that is equal to K3. Let's call it K3 because it's from step 3. And then we're going to multiply that by the concentrations of each of the components. We have H2I and I as our reactants, and so that's what we're going to use in our rate law. All right, fantastic. There's a coefficient of 1 in front of H2I over here, and there's also a coefficient of 1 in front of I, and so I'm not going to write out these 1s, but I'm making the order of each of these 1 because the coefficient here is 1. So actually, you know what, why don't I write it out just to be clear. There's 1s in front here, and because these are steps and not the overall reaction, I can actually drag those 1s down here. That's awesome. So now I have a rate law, and it looks like it's second order, but there's one catch, and it's a big catch. Notice that I have H2I and I in my equation down here, but in order to compare it to my rate law up here, it has to have the same reactants as you see here. So it needs to have H2 and I2, but I have H2I and I. Oh, sorry, neither of those are in my equation. So what I have to go back and do now is to figure out a way to change this concentration number to the concentrations from my overall reaction. So let's dive into this. We need to substitute H2I and I. Let's start with H2I. Where do we see H2I in our steps? Well, we see it in a couple places. We got it from here, but it's also over here. And it's in the form of this reversible reaction. So let's walk through this a little bit and see what we can find. We're going to go to reaction 2 and write some rate laws for it. So based on reaction 2, that's an N. Based on reaction 2, let's do the forward rate law first. So as written, it looks like this. H2 plus I is going to form H2I. Notice, however, there's an equilibrium arrow, which means this reaction can go forward and backwards. All right, so we'll get back to that. So rate is equal to K2. And again, we are just going to use the coefficients from each of our reactants. We have H2 and I. There's a 1 and a 1, so we don't even need to put anything. That's our rate law forward. But notice that this rate law doesn't actually help us. That doesn't include the H2I we're trying to get rid of. Well, we can work with this. We can also say that because this is at equilibrium, the same as H2 and I are being used or formed at the exact same rate, product is being used or formed. So we can write a rate law in the backwards direction. So let's write this reaction backwards just to be absolutely clear. So what you see now is that our reactant that we're going to look at is H2I. So let's do this. Our rate law only includes our reactants, but because this is backwards now, so remember, this is reaction 2, this is just reaction 2 written backwards. Because it's backwards, we're only going to include our reactants. Oh, by the way, and we're going to call this K minus 2 because it's backwards. And then we can put H2I right there. Now, the whole reason we're doing this is because at equilibrium, the forward rate is equal to the backwards rate, right? Forward rate, backwards rate. So we can set these two things equal to each other. Let's first write out forward rate. We can tilt it over here. There we go. Forward rate is equal to backward rate. And now let's sub in what we have here. We have, for our forward rate, we found K2 times the concentration of H2 times the concentration of I, and we can set that equal to K minus 2 times the concentration of H2I. And since our goal is to get H2I out of our rate equation here, we can solve for H2I down here and then substitute that in and see where that gets us. So let's go ahead and do that. Bring out a new page now. So to solve for H2I, as I try to straighten my page here, to solve for H2I, we should find, I'll move H2I over to the left side, and then I'm going to divide by this K minus 2. So we're going to have K2 divided by K minus 2, and then that's going to be times the concentration of H2 times the concentration of I. So what we can go back and do is we can take our rate 3 and substitute this in. We found earlier that rate 3 is equal to K3 times H2I times I. We can substitute this in, and we'll put it in there. So I'll make a little arrow. Our rate 3 becomes this. K3 times K2 over K minus 2 times H2 times I, and we'll close our parentheses, and then we've got another I over here. All right, let's keep on going. Let's simplify this up a bit. Just for the sake of organization, let's put the K2s in front of K3. So it'll go in order K2, then K3. And also we have two i's, the concentration of I times the concentration of I, so we can call that the concentration of I squared. Alright, so we have our K2, and let's just put K3 up top here. We got K minus 2 down there. Now we have the concentration of H2 times the concentration of I squared. Alright, so what order has this become now? If you said third, you were right. But there's a problem. Let's go back to our rate law from the previous page. First of all, we don't want this to be third order. But remember, we have to have this in terms of H2 and I2. We now have it in terms of H2, but look at this pesky I over here. We need to change that. So let's solve for the concentration of I and try to substitute in I2. So let's go back to our 3 steps. We've used equation 2. We're dealing with equation 3. We haven't touched yet is equation 1, and it deals with I, so that's going to be perfect. Let's bring that down and finish this problem out. So here we will write from reaction 1, we see that I2, nope, where did the H come from? Mysterious. Okay, we have I2 and it's transitioning over to 2I. Okay, no problem. Let's write out some rate laws now. The forward rate is going to be, oh, what am I doing here? Okay, I'll just write it that way. The forward rate is equal to, we'll call it K1 now, since we're dealing with step 1, and it's simply times the concentration of I2. All right, no problem there. And our backwards rate is going to be equal to K minus 1 times, K minus 1 times the concentration of I. And again, we're going to use our coefficient, but in front of I is 2. Well, that means we have to put a squared over here. Recall that our forward rate is equal to our backwards rate. So let's sub these in. We are going to find that K1 times I2, the concentration of I2, is equal to K minus 1 times the concentration of I squared. Now here's where paying attention is going to save us a good amount of time. Well, what I could do is I could solve for I could take the square root so that I only have the concentration of I, but look up here. I actually have an I squared sitting right here. If I don't want to take the square root here, I don't have to. So what I'm going to do instead of taking the square root, as I did when I solved this problem on my own earlier, is just solve for I squared. And if that didn't make sense, just watch what I do, and hopefully it will. So we're going to solve for I squared. I'll just keep the concentration of I squared on this side, and we'll say on the other side we have K1. We're going to divide both sides by the K minus 1. So we have K1 times divided by K minus 1, and we still have the concentration of I2. So let's take a look. What we can go back and do is substitute this region, and we're going to go back up over there. All right, so we can take everything on the left side of this equation and substitute it up here where we had I squared. So let's do that. So the rate of our rate determining step is equal to we already had K2, K3 divided by K minus 2, and we had H2. Now we're going to throw in some giant parentheses. We found K1 over K minus 1 times the concentration of I2. All right, now let's clean this up a little bit. We should find, finally, that our rate is equal to, we'll bring the K1 up front and on top, so you've got a nice K1, K2, K3, and on the bottom we're going to have K minus 1, and we're going to have K minus 2, and next we have the concentration of H2, and left over we have the concentration of I2. Okay, so notice we finally have the same thing as we wanted. And sorry, my video seemed to be getting all blurry for a second there. This is now in terms of our reactants, H2 and I2. H2 and I2. Awesome. What does all this mean? Why are there so many K's? Well, K is a number. It's a constant. It could be any number. We don't know what it is. It's actually not important to us in this case. You could say that it's 4 and 0.9, whatever. That's not actually important, except that you realize that all of this is, you could put it together as a single constant if you wanted. Except the point is, we want to make sure that we have it written out this way so that we can show we understand this process. So let's take a look. There's an implied 1 up here, and an implied 1 up here. 1 plus 1 is equal to 2, so it's second order. Does that match the order we found earlier? Down here, cramped, we see initially our experimental order we found was second order, and so sure enough, yes, this mechanism is valid. This means this actually doesn't mean a whole lot. So we've solved this problem. What can we say about this? How can we explain this? All that we've actually found out is that this mechanism we proposed over here is not wrong. It's kind of exciting. But no, not really exciting at all. It's not even very satisfying. It's like, wow, what did I just solve for? Oh, I figured out that the thing I am interested in is not wrong. Well, we'll take it though. So in any case, that is pretty much everything you need to do for this type of problem, and I will tell you, this is about as hard as you'd like to see. The only way you can make this harder is by including more steps. And one other thing, remember that your slow step is the rate that you're interested in. If I had had my slow step be step 1, then I could have just used this first part and it would have just had the concentration of I2. H2 apparently would not be at all important because it's not in the rate law. So just to clarify that, where did I put that? So if reaction 1 had been my slow step, I would only have had to be concerned with this one over here. And then I could say, oh, well, this is clearly just first order. If you want, you can write the concentration of H2 to the 0th power over here, because obviously it's not having any effect. And if that were true, if that were the rate determining step, then we would say the mechanism did not match. It did not fit. But again, this is just a hypothetical, just talking about other things that could happen. As this problem is written, it does match. All right, so that covers it, again, in like 30 minutes. But now you know everything there is to know about this type of problem. You have become a master. Way to go. If you have any questions, toss them below. If you have any comments, do the same. All right, good luck studying for your exam. I'll see you later.